Hello everyone, welcome to lecture 5 of week 10 of the course Power Network Analysis. This lecture is going to be the second last lecture of the module Fault Analysis, in which we will take up two numeric examples in order to have a better understanding of the different aspects regarding fault analysis that we have discussed in the previous lecture. So till the previous lecture, we had theoretically analyzed the application of Thevenin's theorem and Fortescue's theorem to understand or evaluate the worst case fault current that can occur for asymmetric faults, which can be categorized as single line to ground fault, double L fault, and double line to ground fault. In all these analysis, our preliminary assumption or the most critical assumption was that the pre-fault power network in which these faults could occur. It could also happen for the three-phase balanced fault. The pre-fault power network is assumed to be a balanced network, and that is a big bottom line or assumption behind the application of Fortescue's or Thevenin's theorem. The situation might be different or the analysis might be different if this preliminary understanding of having pre-fault balanced power network operation is not valid. So given that for high voltage transmission level power networks where things are usually balanced, at least in the transmission end, the analysis that we have had, it would very well be applicable. So let's understand more about the numeric aspect of how this Thevenin analysis, Fortescue's theorem, how they are applicable. So what I have here is, as shown in this particular slide, I have a 3-bus power network where the buses are numbered in the square boxes that I am drawing. This is actually bus number 3. I think this has been cut off because of the cropping image aspect. So bus number 1, 2 and 3, these are the 3 buses which are interconnected through 3 transmission lines numbered 1 to 3, 1 to 2 and 2 to 3. And then on each of these buses, there are a set of machines connected. They are essentially synchronous machines, to be specific, if I were to be not wrong, but that doesn't matter. These could be synchronous. They are basically some rotating machines which are connected to this power network. There might be presence of load somewhere in the power network, but given the understanding that this network that we are considering is going to experience some type of fault, so even if the load consideration was to be considered, the pre-fault condition, the load currents won't be that high compared to fault current. So intently the presence of loads have not been considered in this network. We are assuming it to be an unloaded network. That is the bottom line part. Reason, if it were to be even loaded, the normal load currents would be much smaller than the corresponding fault currents that would appear in, and hence their contribution is going to be very small. So that's the reason why loads are not present, because they are considering the aspect of unloaded operation. The network is balanced and there are 4 machines which are connected to the different buses. So at bus 1 we have machine number 1, bus 2 machine number 2, and at bus 3 we have 2 machines, bus number 3 and 4. These machines are interconnected to the network through set of 4 transformers, transformer T1, T2, T3 and T4. These are 3-phase transformers in themselves, where if we look at transformer T1 and T2, the LV side is delta connected and the HV side is star grounded. Same is there for transformer T2. LV side is delta connected and HV side is star grounded. How I am identifying LV and HV? LV is low voltage, HV is high voltage, because essentially when I am looking at the transmission network, it is going to operate at higher voltages, and that is where the necessity of these transformers come in, so the power or voltage gets amplified. And if I look at transformers T3 and T4, the HV side connections are both star grounded, but the LV side connections have a difference. Transformer T3 LV is only star connected, whereas T4 is also star grounded. So the reason I am emphasizing about all this is because when we have to analyze some fault balanced or unbalanced fault in this power network, on this three-phase balanced power network, the connections of these transformers, it is going to significantly affect the zero sequence network or the zero sequence diagram of the corresponding network. Also, the way the machines are connected, that is like machine 1 neutral is star grounded, machine 2 neutral is only, neutral is ungrounded, it is star connected, whereas machine 3 and 4, they are also star connected, but 4 is neutrally ungrounded, whereas 3 is grounded through some reactance Xn, whose value we'll see in the next slide. So these aspects of how the grounding is there for the machines with respect to the neutral is also going to affect the zero sequence network. The respective line parameters, they are not given. What otherwise is given is that we directly know what is the positive sequence admittance matrix of this network. And remember, when this positive sequence admittance matrix is evaluated specifically for fault analysis, then the bottom line for this evaluation, one could think, oh, does it mean that Y bus 1 is only corresponding to the parameters of transmission lines, which is the usual case in power flow analysis? No, for steady state analysis, we focus only on the lines, but when we are considering fault analysis, the machine's internal reactance, which is XD dash values, as well as transformers leakage reactance, they have also been considered while evaluating specifically these diagonal terms. And that's the reason where you would see that if only the transmission lines were to be considered, the off-diagonal terms should add up or negate the diagonal terms, which is not the case in either of these three diagonal elements. The reason is the machine's XD dash or XD double dash, to be precise, subtransient reactance, as well as transformers leakage reactance in all the cases have been incorporated in this bus admittance diagonal terms. Zero sequence network, negative sequence admittance is given to be same as positive sequence admittance matrix, and the zero sequence admittance matrix is also given, wherein this zero sequence admittance matrix significantly depends on how these neutral connections are and how the transformers are connected on each of the three buses. And that is essentially the reason where you would see that again in zero sequence admittance matrix, the off-diagonal terms, they don't add up and negate the diagonal entry, which otherwise would have been the case in case we have only three lines whose front conductances as susceptances are not considered. So directly the positive and negative sequence, zero sequence, negative sequence and positive sequence admittance matrix has been given. And now comes the statement that the neutral of machine 1 is solidly grounded, as I have mentioned in the previous slide. The machine 2 and 4 are neutrally ungrounded, as shown over here through the star connection. Neutral of machine 3 is grounded through a neutral reactor Xn, whose value is not known. During some fault at bus number 3, which is the bus shown over here or marked over here, some fault has occurred at bus number 3, and after that fault occurrence, the post-fault phase voltage at bus 1 in per unit, they are given. So VA1, so VA here, A refers to the phase, whereas 1 refers to the bus number. So phase voltages, post-fault phase voltages of bus 1 are given as given in this question. And it is also mentioned that if we have to do sequence analysis of Fortescue's theorem application, we should use phase A as a reference for sequence components. So essentially, we have the information of the network in terms of Y bus 1, Y bus 1, Y bus 2, Y bus 0. The neutral connections, the way they are connected are also mentioned, and there is some fault at bus 3 for which these are the phase voltages in bus 1, and you have to choose phase A as a reference for sequence components. So let's see what the next bit of the question is. The first bit of the question says, draw the zero sequence impedance diagram of the system with all impedances. We don't have to mark their corresponding numbers or values of the impedances, because essentially that information is not known to us. What we otherwise know are the admittance matrix elements. So I'll probably explain for one such interconnection, and then probably we'll see what the other networks or impedances would look like specifically from the zero sequence admittance perspective. So if you recollect that if we had a star delta and star grounded transformer, which is the case for transformer T2 and transformer T1, and suppose the reactances of such a transformer is, let's say, XT, the leakage reactance in the zero sequence perspective. So if we have on the LV side delta and HV side star grounded, which is LV and HV here, then if I denote the LV terminal and the HV terminal while drawing the zero sequence impedance diagram or circuit diagram, wherein ground acts as a reference, whereas for positive and negative sequence networks, the neutral can act as a reference, and there is a big difference between positive, negative and zero sequence network connections. So coming back to the zero sequence representation of this transformer with HV side being star grounded and LV side being delta connected, if you recollect or revisit our discussion where we have this JXT representing the zero sequence leakage reactance of the transformer, then how should this connection look like? Remember, in delta connection, the zero sequence current can never escape out of the terminals. It can only rotate or be present in the circulatory fashion within these three phases. So there it is. So in order to not have any zero sequence current on the LV terminal, the only possibility for this connection of current to exist is that on the LV side, the JXT is grounded to the ground directly, whereas in the HV connection where it is directly star grounded, we have the connection as shown over. So essentially, whatever zero sequence current can be present on the HV side, it would be present in the winding on the HV side, and instead of leaking out of the LV current, LV side where I0 is the zero sequence current, it would pass through the ground and again return back to the circuit. So if you recollect this particular discussion that we had for zero sequence impedances of transformers and lines, then the corresponding zero sequence impedance which would be like this. So for ZT2, I have specifically discussed this. Same would be true for ZT1. For machines which are solidly grounded like generator 1, then the corresponding reactance value would be directly connected to the ground, whereas for machine 2 and 4, they neutral are ungrounded, so there won't be any possibility of zero sequence current be present on this particular element, as well as in this entire circuit, because there is no path for zero sequence current to flow. Only for generator 3, there is a solid path from bus 3 to the ground for the zero sequence current to flow either inward or outward. And for transmission lines, their corresponding reactances are as usual present. So we don't know what these Z values are, but it's just a symbolic representation. I hope this discussion is clear. The next bit is which fault has occurred at bus 3, because it was already given that fault has occurred at bus 3. Now we have to identify what is that particular fault. So given that phase post-fault voltages of bus 1, they are given A, B, C, and remember phase A has been given or told as reference for sequence components. So if you recollect, VABC is nothing but capital A matrix time of VA012. So where A is the matrix that we discussed in Fortescue's theorem or sequence network discussion. So if you apply that capital A matrix, basically if you want to find VA012 as shown over here for bus 1 with phase A as a reference, then you have to do A inverse of VABC. So if you do that, you get this particular information. And since the sequence voltages at bus 1 are now known, so it is imperative to get some information out of this using the corresponding impedance matrices. So since Y buses are given, we can take their inverses and get the corresponding impedance matrices. Why these impedance matrices are going to be important? So the first aspect is application of Fortescue's theorem, whereas impedance matrix evaluation would be application of Thevenin's theorem, where we have to find the corresponding Thevenin impedance between the fault point and the ground where the fault has occurred, or the neutral point where the fault has occurred. So essentially the reason of finding these Z buses is to look at or gauge bus 3 from these sequence voltages given for bus 1. Similarly, Z bus 0 can be evaluated by its inverse, and since fault has occurred at bus 3. So in terms of change in injection currents, the change in the injection currents would only appear for bus 3. That means if I have to denote I0 vector for bus 1, bus 2, bus 3, then this vector being a 3 cross 1 vector. For bus 1, these 1 and 2, these quantities would be 0, whereas for bus 3, this would be a non-zero quantity. So essentially by using, and since there is no change in sequence currents at bus 1 because the fault has not occurred at bus 1 and 2, so we can make use of the corresponding V01 expression in terms of the corresponding Thevenin impedances, which is what is the element shown over here. So Z130 is the 1 comma, sorry, it is the 1 comma 3 element, which is J0.05. We'll be using that particular expression and trying to equate bus 1 zero sequence voltage to find the non-zero current which I was talking about in terms of the zero sequence current at bus 3. So by doing so, we can find the sequence currents which are non-zero at bus 3 because for other buses the fault has not occurred. So by using the corresponding zero sequence network, positive sequence network, which is an active network, and that's the reason why for zero sequence there is no source present. For positive sequence network, we have an active source. Since the network is unloaded, so V1 pre would be equal to 1 at an angle 0 degrees. And similarly for V21, which is negative sequence network, we have a passive network, so we can find I23, I13 and I03. Now when we look at these three currents, what appears is that the corresponding sum of these currents are 0. Now in which type of fault the sum of these three currents were 0? Definitely there is an involvement of zero sequence current because zero sequence component is not 0. So it is definitely going to be a ground fault. There are two possibilities of asymmetric ground faults, which are line to ground fault or double line to ground fault. In case of double line to ground fault, we have seen that the sum of these three sequence components is 0. So it's truly a case of phase to ground fault. Now, which phases are involved? Since we have taken phase A as a reference, and typically when we choose phase A as a reference, this beautiful addition or equation is applicable for phase B to C to ground fault. So fault at bus 3 is a B to C to ground fault. That covers the second bit question. You can again cross verify the statement that by adding sum of phase currents, the numbers do satisfy. The next bit is what is the fault current and impedance at bus 3? The fault is definitely a B to C to G fault at bus 3. Now we have to find the current and impedance. So from solution of the previous bit, the fault is phase B to C to G ground fault, and the corresponding sequence network for double line to ground fault, we have seen this part here is the positive sequence component. This part here is the zero sequence component. This part here is the negative sequence network or representation, and double line to ground fault, positive and negative are parallel and they're in anti-series to the zero sequence network. So we know this for sure, so we can draw this circuit. Now in this circuit, what is not known is the value of this fault impedance. Since we know the corresponding other quantities, we can very well evaluate this 3ZF connection value by a simple KVL. So from the network, ZF is J.1 PU, and for fault current in double line to ground fault, it is 3 times of the zero sequence current. Since we know this value, so we can find the corresponding fault current value. That covers question number 1. Now, I have another question which is relatively simpler in terms of having just a 3-phase balanced fault. Again, there are 3 buses, and across bus 1 and 2, 2 generators are connected. The transformers T1 and T2 are having dissimilar configuration. Both machines are neutrally grounded, and the positive and negative sequence impedances of each of these elements, G1, T1, line 1, 2, 2, 3, 1, 3, T2 and G2, they are given over here on a common base. The neutral of the machines, they are grounded through a neutral reactor of 0.05 per unit. Neutral of HV side transformer is solidly grounded. Neutral of transformer T2 is ungrounded. And the system is, it's given that the system is operating at nominal rated voltage without pre-fault current. That means this also is a unloaded network condition. All resistances and shunt capacitances are to be neglected. The question says, Draw the positive, negative and zero sequence impedance diagram with all impedances marked appropriately. So if you draw the uh, positive sequence network, which is likely going to be same as the negative sequence network, wherein each generator is represented by this internal EMF. Since the machine is unloaded or network is unloaded, so all voltages are at 1 at an angle 0 per unit degree, and the positive sequence impedance is same as the subtransient direct axis transient reactance of the transformer. The positive sequence impedance network, it looks like something like this. The generators are represented by their internal EMFs, which I was also talking about in context of question number 1, and the corresponding subtransient reactances are important. Transformers leakage reactances, the way they are given, they will remain the same. And also I'll have the line reactances as given in the data sheet. The negative sequence impedance diagram will exactly be the same as the positive sequence impedance diagram. The only difference is that in negative sequence impedance diagram, these sources won't be present, which is essentially what is marked over here. The generators transient EMFs, they would be short circuited, they won't be present at all. For zero sequence impedance network, the discussion that we had for transformers with dissimilar configuration and the corresponding way the neutral are grounded for the machines, we will have either flow of zero sequence current or no flow of zero sequence current. So in this context, if I were to say there is no direct path in this circuit for zero sequence current to flow, neither there is a path here for the zero sequence current to flow. So zero sequence current contribution from generators will never ever come in if some ground fault occurs at bus 1, 2 and 3 in this particular network. The next bit is find the positive, negative and zero sequence impedance matrices for the system buses. The positive sequence admittance matrix, depending on the circuit that we have understood here, we will be correspondingly evaluating the machine's internal reactances and leakage reactance to find Y10, Y12 and 13 they pertain to the line parameters, Y23 also pertains to line parameters, whereas Y20 is the connection of the machine's internal reactance, transformers leakage reactance as well as the ground with respect to the bus. So once we know these Y elements, the Y bus evaluation remains the same, which is as shown over here. The negative sequence admittance matrix will be same as the positive sequence admittance matrix. Only difference is that in the network of negative sequence matrix, sources won't be present. The zero sequence admittance matrix will depend on how the transformer connections are and how the neutrals are connected. So if we look at the zero sequence impedance or network, bus 1 has some possibility of flow of zero sequence current, not from the generator but through the transformer. So we'll have to consider Y10, which is going to be the inverse of this element. Whereas if we look at Y20, the Y2 part is left hanging with respect to neutral, so Y20 won't exist. For bus 3, there is no information given, the load is considered to be unloaded. So only Y10 term would come in, and additionally we will have Y12, Y23 and Y13 while evaluating the zero sequence impedance matrix for the given network. So that's the reason why only Y10 is given, whereas other line parameters are the line parameters. So once we get these Y values, the corresponding Y bus evaluation remains same as discussed in power flow analysis or the way the corresponding Y bus 1 was evaluated. With this inverse, we can find the zero sequence bus impedance matrix. The next bit is that at bus 3, a 3-phase bolted fault has happened and we have to find the LV side fault current contributions from generator G1 and G2. So if I go back and look at my circuit for a moment, what is given here is that in this network, a 3-phase bolted fault has occurred. That means all the 3 phases are equally getting shorted at bus 3. And for this 3-phase fault, I have to find what is the current contributions from generator G1 and G2. Now, since this is a 3-phase balanced fault, so it is imperative that the negative and zero sequence networks won't play any role at all. And that's the reason why only the positive sequence network comes into picture. For the pre-fault unloaded situation where V3 is 1 at an angle 0 because that's the unloaded situation, and Z331 being obtained from the corresponding positive sequence bus impedance matrix, we can find the corresponding fault current for 3-phase bolted fault, which is this number. And with this fault, now we can try to find the corresponding positive sequence voltages at all the buses. So bus 1, so first number is for bus 1, second is for bus 2, and third is for bus 3. Since bus 3 is solidly grounded, its terminal positive sequence voltage is perfectly zero. The post fault negative and zero sequence components are perfectly zero because these currents are zero, they don't exist for balanced fault. Now, once we know these sequence voltages, we can convert them to corresponding phase voltages. But before doing that, since we have to find the LV side current, so it is always suggested that retain your evaluations in sequence network or sequence component to the extent possible, because sequence component would be easily able to encounter the phase shift that would occur because of dissimilar transformer configurations. So we will evaluate the line currents using these sequence voltages only. We will not convert to phase domain yet. So you find the corresponding positive sequence line currents IA12, IA13, IA23. Other line components are perfectly zero. Once we know the corresponding line currents, sequence currents, on the HV side of transformer, where bus 1 is, so basically what we have found is, if I have bus 1, 2 and 3, I have been able to find IA13 positive sequence current, IA12, which is the positive sequence current of bus across line 1, 2. And if these currents are flowing, then this is essentially the current present on the HV side of transformer, which is by KCL I get this number. And hence I have this as my generator HV side current. Other sequence currents, since they don't exist, they are perfectly zero. Similarly for G2, I can apply KCL, where G2 is the current flowing over from here, and this is IA231 and IA211. So once I know my HV side current on the positive sequence perspective, other components are zero. Now I should apply the corresponding phase shift, because the transformers are delta and star. Star on the HV side, and again here star and delta. So LV side is the delta component, and when we move from the HV side being star, go to the LV side delta, these currents will have a phase shift of additional 30 degrees, minus 30. So the correspondingly LV side currents are these components. Other sequence components don't exist because they never existed on the HV side of the transformer also. And once I know these sequence components with zero other components, now I can transform them back to the phase network or phase component, where IABC for a given bus is A times of IA012. So A matrix is the same matrix that we had discussed. So these are the corresponding current contributions from the LV side of transformer. Which is a bit interesting to note here is that the fault has occurred on bus 3, which is a balanced 3-phase fault, and even though there is no physical flow of zero sequence current from generator G1 and G2 on the network side, still the 3-phase currents, they are existing, and these 3-phase currents are again in a way balanced currents. So the last bit is that for a phase to ground fault at bus 3, we have to find the post fault voltages at bus 1, bus 2 and bus 3. Is just a enumerated combination that is just given here. So assuming phase A as a reference for A to ground fault, all the sequence networks or components would be in series. We know the impedances, we know the pre-fault voltage, so we can find the corresponding sequence currents. Once we know the sequence currents, we can apply Thevenin's voltage to find the sequence voltages. So this is positive sequence voltage. Similarly, I have negative sequence 3-phase voltage and the corresponding zero sequence voltage for all the 3 buses that are there. Once I know the voltages, I can then correspondingly apply the transformation back to phase voltages. So for bus 1, which is where I have to find the phase A voltage, so I'll simply add the phase components or the sequence components, because phase A itself has been chosen as a reference here. So I'll simply add the positive sequence component, negative sequence component and zero sequence component for the 3 buses given here, and I'll simply be able to get phase A voltage. For phase B, I have the A operator coming in, where A is at an angle 120 degrees, and similarly for phase C. So that is all from my side for the discussion behind the solved examples that we have discussed. Hopefully this has given you enough understanding of how balanced faults, unbalanced faults are analyzed using Fortescue's theorem and Thevenin's theorem. The next lecture is going to be the last lecture of fault analysis module, where I'll briefly talk about the challenges that that do exist with lot of renewable energy resources being integrated into the power network. By renewable energy resources, my focus is mostly on solar PV plants, wind generators, and all other possible inverter based sources, that is sources which can be connected. So inverter, let me write it first. Inverter based resources, all such sources which need to have this inverter connection in between before they can be connected to the AC grid. What challenges do they pose in terms of power network protection, wherein fault analysis is one such simple or small exercise that we do. So hopefully you will be able to get some vision of what these challenges are. So that's all. Thank you so much.